So welcome back. Today we're going to get started in on really some of the nuts and bolts of structures. And having looked at some history, having looked at some case study, we're going to start trying to figure out ways that we can actually model structural behavior. We need to find ways to take what goes on in nature and turn it into something that we can manipulate, something a little bit mathy that we can play around with and understand in terms of numbers instead of just in terms of concepts. We won't go too deeply into the weeds with this. All you'll need to know in terms of math are a little bit of algebra, some trigonometry maybe, but we'll try to keep it simple. And the good news is that a lot of the math involved is the sort of math that architects are kind of good at: geometry, triangles, things that are more or less kind of spatial. And we'll use these mathematical ideas to get at what we call forces and loads, or the way we'll do it actually is going to be loads and forces. Loads are things that occur in nature. Forces are mathematical entities that we can manipulate and move around. And we'll talk in the next couple of lectures about how we take loads that happen in nature, figure out how to treat them as forces that occur only in our head in math, and then we'll look at basically how we can manipulate forces to get the end result that we want, which in the case of structures is buildings that don't fall down, don't fall over. Okay, sound good? Awesome. So in this first video about loads and forces, we'll talk a little bit about the types of loads that occur in buildings. We divide those up in a couple of different ways: live loads versus dead loads, distributed loads versus point loads. And then we'll talk about how we think about those as forces, these geometric or mathematical entities that we can use some math to manipulate and move around. We'll then talk about equilibrium, and equilibrium is like the magic thing that structural engineers and really we're all after. We don't want our buildings to move in any directions. We don't want them to fall down. We'll call that translational equilibrium, but crucially, we also don't want them to fall over. And this is a different kind of equilibrium called rotational equilibrium. And then we'll finish up talking about loads and forces by doing some exercises, some thought experiments, but some actual exercises where we want you to experience what compression, tension, bending, shear, some of these things feel like. So we have an exercise called Body Labs where we'll suggest some kind of yoga poses and things where you can actually feel the forces that are going on in a building in your own body, in your own musculature and skeleton. So to start with, let's think about what we're trying to hold up, essentially. And building structures have a whole bunch of jobs to do structurally. They have to hold up a bunch of different stuff. Some of that stuff is actual building itself. Some of that stuff are things that are inside of the building, and some of that stuff are things that happen to the building, environmental forces. The technical definition of a load is a weight or source of pressure that's borne by someone or something. In other words, it's a little bit of a circular definition. A load is anything that requires a structure. Any force doesn't have to be a weight, and we'll certainly talk about forces from things like wind and earthquakes that don't have any actual mass, but nevertheless put significant pressure and therefore significant loads onto building structures. Generally, we will refer to it as any force that's imposed on a building structure, any pressure, anything that would cause a building to fall down or collapse, basically. And we talk about these in two general ways. We talk about them in terms of what are called dead loads. These are immobile. They're part of the building. They are fixed to the building frame, and we can be pretty sure that they are going to be there for the lifetime of the building. Dead loads are relatively easy to deal with. We can calculate how much concrete, for instance, goes into a building frame. We know pretty well what concrete weighs, and therefore we can calculate the total load that the building frame puts on itself. But anything that is attached to, fixed to the building, that's not going to move over the lifetime of the building, or that's going to require some real effort to move it, we think of these as what we call a dead load. And we calculate these in one way that we'll talk about in later classes. The other type of load, the one that is much more difficult to estimate and the one that very often gets us into trouble, are what are called live loads. And these are transient loads. They can be moving around the building. They may be there one day or 1 minute and not the next. Anything that puts pressure onto a building frame that is not permanently attached to the building structure is a live load. And so dead loads are typically the structure itself, partitions, fixtures, things like that. Live loads are anything that happens to the building. So you are a live load in whatever building structure you're in now. You are moving around. Your weight is being borne by the building structure, but it's being borne in different places at different times. If you get up and go get a sandwich, or if you get up and go get a drink of water, your load, your weight, your mass is going to affect the building structure in subtly different ways. In addition to people, things that people sit on, chairs, sofas, tables, these move around and they may be there one day, they may not the next. So furniture counts as a live load. Storage is one that often gets to be problematic. We sometimes have a case where we design a building for one type of function and it ends up being used, for instance, to store lots of books. Book storage is one of the heaviest live loads that we typically deal with in architectural structures. And if clients put very heavy books into a room that we hadn't designed for it, this can cause understandable problems in a building structure. The things that actually get, I think, more interesting and more complicated are the forces that happen to, or the loads that happen to a building from outside, where we may not be able to fully calculate all of the external loads that are going to happen to a building over its lifetime. Environmental loads like wind or snow or water. These can range from relatively modest to really intense. If you're designing a building in Miami, you typically design it for hurricane force winds. And winds, of course, have no mass, they have no weight, but they can put significant pressure onto a building. And building frames have to be designed to take loads from hurricane winds that may not just tip the building over, but actually may try to pick the building up. So environmental loads are unpredictable. They can be really extreme. And depending on where you are in the country, you may find yourself designing for all kinds of odd structural situations that you wouldn't be designing for elsewhere. Another really, really big one that we don't worry about so much in the Midwest, but certainly designing in California or in the Middle East or Asia, we worry about quite a bit, is seismic. Seismic loads are loads that come about usually from the momentum of the building frame itself in an earthquake situation. So building frames are heavy, they have a lot of mass, they have a lot of inertia, and when the earth moves underneath them, the tendency of the building frame to stay in one place while the earth moves underneath it often creates this whipsaw effect that can put very, very serious and often unpredictable loads onto a building frame. Some of the other ones that are maybe a little bit more minor that we might not ordinarily think of, but that can cause all sorts of issues that have to be thought about when we're designing structures, are things like thermal loads. Materials expand when heated, they contract when they get cold. And so a building frame that is enclosed by a curtain wall, we may find that there are significant loads that the curtain wall imposes on the building frame. The building frame stays at 72 degrees because it's enclosed. It might be a hot day out where it's 105 degrees and the curtain wall is going to expand. And if we don't detail that curtain wall correctly, it's going to put expansion loads onto the concrete frame that maybe were unanticipated or maybe locally cause cracking or problems that we should have figured out. Underground, we get all kinds of weird hydrostatic pressures. The weight and the tendency of water to try to fill a void means that in really, really wet soil, we have to design our building foundations almost as if we were designing a boat. And the hydrostatic force of water in the soil can not only leach water into a foundation, but it can actually deform foundation walls if they're not designed correctly. And then finally, two that are maybe less common but can still be important, things like impact loads. We may be designing a secure facility. We may be asked to design it not only against all the kind of forces of nature and live loads and dead loads, but against things like explosions or someone trying to drive a vehicle into our building. And the last one that engineers get really worried about is construction loads. We typically think about our buildings all done and complete, and we can sort of catalog all the likely loads that we think are going to go into it. But what happens when you are driving a concrete mixer around on a floor to get it to part of the job site? Or what happens when your structure is incomplete and subject to wind loads that maybe it wouldn't be when the curtain wall is in place? These are things that structural engineers worry about after the kind of calculations for the building are done, thinking about how the contractor is going to actually put the building together. So one way to think about this is when we're thinking about dead versus live loads. Dead loads are essentially, I like to think of it as anything that we draw in a heavy line, right? Anything that is permanent and fixed and kind of bulky and unlikely to ever move. So building structure, for sure. Building partitions, will generally count those as dead loads. You might move a partition around here or there, but not very regularly, not many times over the course of a building. And then finally, fixtures. Anything like a light or plumbing, anything that's securely fixed to the building frame that's not really going anywhere. Now, opposed to that, live loads are anything that you draw in a kind of light line, animation like people or furniture, vehicles, storage, or environmental loads, things like snow loads in the Midwest, wind loads in Miami, seismic loads in California. These are all loads that occur either intermittently or that move around the building. We have ways of estimating these that building codes typically give us, but we never really have any way of knowing exactly for sure every live loading condition that a building is going to experience. We go to rules of thumb, we go to building codes to estimate what these might be. And we'll very often do two separate calculations, one for the dead load itself, the weight of the building itself, make sure that the building can support its own weight, and then another one where we'll go to the code or a reference book and we'll look up the live load for the use that we're designing for. So for example, a library, believe it or not, will often have a much heavier live load than a house or a school or even an office building. That's because libraries store books, which are very, very heavy and very, very dense, especially if there's something like compact shelving being used. An office building might have a live load of something like 60 or 70 pounds a square foot. A library might have something more like 100. We think about loads too in terms of how they are configured, and this will start to be really important when we design beams and when we design columns. We think about loads in terms of whether they are concentrated, or what we call a point load, or whether they're distributed, whether they're spread out over a structure. This gets important because you can imagine these two scenarios, right? A point load of, say, 300 kilograms or 300 pounds, whatever you want to think of it. Or, what happens if you put that load on one point in the structure versus what happens if you spread it out? Well, think about what is happening to the structure right under that concentrated load. It's trying to resist all 300 kilograms, the whole magnitude of the concentrated load in a very, very small area. Whereas the distributed load, if you think about every molecule of concrete in that slab, it's only taking a very, very, very small piece of that load. So even though the supports of both of these slabs are going to feel that 300 kilograms, the structural element itself is going to behave very, very differently. And so as we're thinking about the type of loading that a building is taking, we want in the back of our mind to be thinking about whether those are concentrated loads or distributed loads. And we'll talk a lot about how we simulate these, how we kind of model them mathematically, and the different ways that we add them up. For the moment, just think about things like an individual person we think of as a concentrated load, where our load is spread out over our feet, but in structural terms, that's relatively small. Something like a chair or a light fixture, even some small pieces of furniture we would think of as a concentrated load. A distributed load would be more like a grass roof, or a storeroom that has boxes spread all over it, where we're really using the full area of a floor, for instance, to spread that load out. And we might think about the total magnitude, the total weight of all of those boxes, but we'll think about it more in terms of the number of pounds per square foot, or if we're designing a beam, the number of pounds per linear foot when we're thinking about distributed loads. So if loads are things that happen in nature, it's great that we can kind of visualize these, understand them, think about them both in terms of whether they are an inherent piece of the building or whether they kind of happen to the building, dead load versus live load. We can think about whether they occur at a discrete point on the building frame, concentrated load, or whether they're spread out, a distributed load. But what we really want to do is we want to find a way to take those loads and to turn them into numbers, right? To turn them into something that we can manipulate with some simple algebra, or as I'll show you, some simple geometry. And the way we do this is we think about those loads in terms of forces. Now, those sound like two names for basically the same thing. In a lot of ways they are. But a force has a very precise mathematical definition and a way of representing it that allows us to sort of take the loads that occur to a building and to think about them in this kind of simulated way, this mathematical way. And we do this through what's called vector geometry, thinking about the loads as arrows and then using some geometry to manipulate those arrows to figure out what's going on both on the building structure and then later on within it. So if you go back to your kind of physics 101, right, a force is an interaction that, when unopposed, will change the motion of the object. Force is related to mass and acceleration. This goes back to Isaac Newton, who realized that to get an object to move, to accelerate, to go from 0 to 1 miles an hour, you have to expend some energy. You have to basically push on it. And that push is what Newton called a force. We measure that usually in pounds. Forces are these mathematical entities called vectors. Vectors are arrows that have a very precise magnitude or length, a recognizable direction, which way the arrowhead is pointing, and a sense whether that arrow is pointing one direction that the arrow is heading or the other, positive or negative we call this. And translating loads into forces is the first step in our understanding how a building structure is going to perform, what's actually happening to it. And structural engineers say how the building structure will behave, basically whether it will carry the load or not, whether it will deflect too much or not. We are trying to put buildings into what we call equilibrium, which we'll talk about next. We're trying to balance basically the forces out. We want to figure out all of the forces that are acting on a building, and then we want to see if we can design ways to oppose those forces, to put vectors that are equal and opposite to every arrow that we're putting onto the building, to ensure that the loads that are happening in the building do not, in Newton's terms, change the motion of our object, right? We deal with statics, not dynamics, and so we always want our acceleration to be zero. As we'll talk about, that never happens. Buildings actually do move around very, very small amount. What we want to do is we want to keep those accelerations really, really low, and we want to find ways to channel forces so that we can build up equal and opposite or reactions to the reaction forces to the loads that are being put onto a building frame. So to do this, we think about what are called free bodies. We reduce building elements down to little tiny points. And we do this little thought experiment where we try to imagine what a load is going to do to that point. So here is our friendly point. We usually call it P. And this point could be anything. It could be a whole building frame. It could be a giant building site. It could be one beam in the building. It could be a rivet or a bolt. It could be any piece, anything that has actual physicality to it. We reduce it to a point to think about just what's happening in terms of the forces acting around it. So we take away all the kind of spatial dimensions. We take away all of the, what it looks like, what it's made out of. We'll get to what it's made out of in the strengths of materials. But we think about building elements, building frames, whatever, as just single points. We call these free bodies. And by doing this little thought experiment, saying that we can reduce essentially anything in the physical world to a single point, we can then imagine what happens when we put a force on it, a force in the shape of a vector. Okay, there is our force, or actually let's call that a load, right? Because that looks like something that happens in the real world, right? The 10-ton anvil comes down and smacks our point P. That anvil is a load, something that happens in nature. But what we do is we translate that into a force. And because the anvil is getting pulled down to the earth by gravity, we know which direction it's going to go. It's going to go toward the center of the earth or toward the ground. And we know how big the force is. It says right there on the anvil, it's 10 tons. So we can replace the cartoon anvil with a vector, with an arrow that says 10 tons, and that has an arrowhead that indicates which direction that force is acting. So it's less amusing than an anvil for sure, a little bit less evocative, but basically we're doing the same thing to the force that we've done with the building element. We're stripping it of all of its kind of real world connotations, and we're thinking about it just in the simplest possible terms. Now, that arrow actually contains a fair amount of information. It tells us the magnitude of the force, 10 tons. It tells us the direction, 270 degrees from zero, and it gives us the sense. It's pointing down. So 3 pieces of information contained in one graphic. Now, what that arrow doesn't do is it doesn't tell us like how big the thing is that's putting the load on the building. It doesn't tell us what color it is or what shape it is. It's abstracted the force completely into just simply this vector. So we've done the same thing with the force that we did with the building. The building we turned into a mathematical entity, an abstract mathematical entity called a point, right? Stripped everything else we know about it away. All the point tells us is position, right? Where it is in space. We've done the same thing with the anvil. We've taken away the shape of the anvil, the size of the anvil, what color it is, what it's made out of. All we've got now is the force that that anvil puts onto point P. Okay, now looking at that, you might think, well, you know, what would happen in the real world, right? If you drop a 10-ton weight onto pretty much anything, if you don't have a way to resist that load, what's going to happen to point P? Well, Newton says force equals mass times acceleration. So if you put a force onto anything, no matter how much mass it has, it will accelerate. It might accelerate very slowly if P is a very, very big thing, or it might accelerate very, very quickly if P is relatively small and light. Doesn't matter to us when we're thinking about structures. We want that acceleration to be 0. And the only way to do this, right, we can't make our mass infinite. All we can do is figure out a way to put an equal and opposite force onto point P, right? To prevent P from accelerating down toward the Earth, we need to come back and we need to think about a vector that is equal and opposite to the vector that's being imparted to that point, in this case from the anvil. When we do that, when we have 2 arrows that have equal magnitude, equal direction, but opposite sense, right? Note that they're both aligned 90 degrees or 270 degrees to horizontal. They're both aligned vertically. Notice that they have exactly the same magnitude, 10 tons, and notice that their sense is opposite, right? One we could call positive, one we could call negative, or one we could call down, one we could call up. Doesn't matter. They're going in the opposite direction. The red arrow, the red vector, is equal and opposite to the white arrow. And so in this simplest possible case, we have a state of equilibrium. P isn't going to accelerate up, it's not going to accelerate down, because the force that we're putting on it is met by an equal and opposite force. All right? We will stop there. We'll talk about equilibrium in more depth in the next video. We'll talk about not only how we think about equilibrium in terms of translation, up, down, left, right, but also in terms of rotational equilibrium, whether our building is spinning around or not. That may sound a little ridiculous, but it actually, as we'll see, has real applications when we're talking about things like beams. For the moment, just remember that loads are things out in the world that happen to a building. We think about those in terms of what's attached to the structure, or is the structure a dead load, versus things that happen intermittently to the building, which is live load. We have these two types, distributed versus point, or distributed versus concentrated. And then we take those loads and we turn them into arrows, forces that have magnitude, direction, and sense. And now, with those definitions in mind, we'll look at how to arrange our arrows basically to keep free bodies, to keep little points P in one place, and also to keep them from spinning around. That'll be in the next video on equilibrium.